So far we've talked about how systems handle energy and the difference between closed systems and open systems, and the fact that open systems lose or gain external energy that leads to work done on or by the system. And you can see in this photograph of this infrared photograph of the house that there is some energy being lost rather. And when we look at this in terms of an energy flow diagram of the house being the system, if you like, in physics terms, we can see that there is some heat being lost right around here, and that heat is being lost out of the system to the air, and we can see that in the image above. Now the question is, well, a couple of questions. First question is, do all materials gain or lose heat energy in the same way? The second question we're hoping to answer today is, can we represent this quantitatively? Okay, let's take a step back before we take a step forward. This has some real practical applications when we discuss thermal energy. So, quick question for you to ponder. It gets quite hot in Toronto in the summertime. There is lots and lots of little fishies in Lake Ontario, as in many lakes. And the question is, why these little fishies here swimming along do not take that sun's energy and just simply fry. So what is it about the water that provides a protective guard? And just through our actions, we would probably be able to say that the heat would give the surrounding areas surrounding the water a higher temperature, sand, ground, and so on, a higher temperature than the water, which would actually remain at a lower temperature. Similarly, we've seen that when we heat, a pot of water or whatever, we use certain instruments in terms of spoons and whatnot to make sure that we don't actually get burned. So, we have protective coating on our spoons to make sure that we don't get burned. And the question is how we can represent that insulating property, or that property of materials that resist the heat being transferred to the material and the temperature of the material going up too quickly. So the next thing, before we get to talking about this, the next thing that I want to talk about is just to get settled on a few definitions. First definition that we need to discuss is temperature. Now, it is important to know that we probably have an incorrect understanding of temperature. Temperature is simply the average kinetic energy of particles in a material. And if we look at a basic thermometer, what happens is the molecules inside the thermometer, those red molecules inside the thermometer, they actually, as they get hotter, that kinetic energy starts increasing, and what we get is we get more movement and more movement of those molecules, and it causes the liquid in the thermometer to actually go upwards. So thermometer is a good representation of that. It's the temperature is the average kinetic energy of the particles. Thermal energy, however, is the sum of kinetic energy and potential energy of the particles in a material. So the more kinetic energy there is, and the more potential energy that's stored in these bonds, the more thermal energy of a material. The third thing that I'd like to talk about is heat. Now, very often we look at heat as something that's a noun, that is a thing. Well, heat is actually just the energy transfer from a warmer body to a cooler body. So heat is not a noun or a thing per se. It is the heat difference, or energy transfer from a warmer to a cooler body. So how is heat transferred? Well, we're familiar with some of these terms: conduction, convection, and radiation. You probably have an understanding of those. These are three different methods that heat is transferred. In other words, energy is transferred, and we see that as heat. Conduction is normally associated with solids, convection with liquids, radiation with air, gases. And if we take the example of conduction, the hand in this diagram is about to touch the heated pot. Now, we would hope that this pot is made out of certain materials, and we know from our experience that if we touch this pot handle, if we touch the handle here, if it's metal, metal does a great job of passing that heat onto our hand, which wouldn't be too good for us right then. And so that metal has taken on the heat, the energy of the pot that was given to the pot, and it has gone up in temperature quite a bit, and our hand will feel that. So it's safe to say that depending on the material of the handle, we will notice that increase in temperature of the handle, and whether it goes up in temperature a lot or a little. So wouldn't it be good to have a measurement for how a material handles an increase in thermal energy? Do you like what I've done there? How a material handles? Of course you do. An increase in thermal energy. There is a property in physics and indeed chemistry that discusses how a material increases when given thermal energy, and that is called heat capacity. So the heat capacity is the amount of thermal energy required to increase the temperature of an object by 1 degrees Celsius or 1 degrees Kelvin. Now, specific heat capacity is the same. It is also the amount of energy needed or required to increase the temperature, but it's more specific. So it's to increase the temperature of, I'm just going to color code this, of 1 kilogram of an object by 1 degree Celsius. So 1 kilogram. And in chemistry, sometimes you'll see that as 1 gram. In physics, we like to use 1 kilogram. And so if we look at the photo below, if we're talking about a copper spoon and a plastic spoon, I think we would agree if they put in warm water that the copper spoon would increase in temperature much quicker for the same given amount of thermal energy than the plastic spoon would. So we're going to now relate that to an equation which will show how we would show the different specific heat capacities of these materials. So when we talk about specific heat capacity, there's a very important famous equation that we're going to look at in terms of, we will see it in physics, we will see it in chemistry. And when we talk about specific heat capacity of a material, it is the change in temperature of a material when it's supplied by a certain amount of energy. So it's a relationship, if you like, between the energy added or removed from a system in joules for 1 kilogram of substance, and it is the energy that's added or removed required to heat 1 kilogram of substance by 1 degrees Celsius. And so specific heat capacity takes on the units of joules divided by kilogram per Celsius. Now, sometimes we see this very often manifest as Q is equal to mc delta T. In other words, the thermal energy added or removed from a system is equal to the mass times the specific heat capacity times the change in temperature. So what does this mean in the real world? Well, the specific heat capacity will have a low specific heat capacity, a low value for C, if it has a big change in temperature for minimal thermal energy added. So we see this with materials like copper, materials that are good conductors, metals normally. And a high specific heat capacity means that a small change in temperature is seen for large thermal energy added. So a lot of thermal energy needs to be added to get a shift in temperature. And we see that for good insulators, and water is a good example of that. And this is why the fishies in Lake Ontario do not fry to death in the summertime, because the water is protecting them. It doesn't increase in temperature in a major way, even though the thermal energy from the sun is quite large. So different materials have different specific heat capacities, and just looking at a couple of them, the two that we've already highlighted are copper and water. You'll notice that water has an extremely large specific heat capacity. It's one of the really cool properties of water. And copper has a specific heat capacity which is greater than 1,000 times lower. So it will jump up in temperature or down in temperature much more in relation to energy being added to it. So let's look at a sample problem now if we can. And the sample problem is how much energy is needed to raise the temperature of 1.8 kilograms of water from 10 degrees Celsius to 80 degrees Celsius. Well, so if we look at this practice problem, a very good example, a very good idea first is to start underlining our givens and start writing out our givens. So if we start writing out our givens, we'll see that the mass is 1.8 kilograms. We would need to be given a specific heat capacity of water or have a chart as a reference, and we would know it's a very common one that it's 4.18 by 10 to the 3 or 4,180 joules per kilogram per Celsius. That's a standard value for water as found by scientists way back when. The initial temperature is 10 degrees Celsius. The final temperature is 80 degrees Celsius. So we know that that change in temperature is 70 degrees Celsius. So it's TF minus TI. So it will be a positive 70 degrees Celsius. Oh, my positive is a bit off there. And what is required? Well, we're being asked for how much energy, how much heat energy. So that is Q that we're actually required to get. And if we look over in terms of, so we put it into the formula, Q is equal to MC delta T. We'll see that the Q value is what we're looking for. The mass is here, the C value is here, and the delta T is here. And we get a value in joules, 526,680 joules. So that is, if you like, how much heat energy was needed to raise the temperature of water from beginning temperature to a final temperature. So what we looked at was quite an easy sample question where you could use that equation to find, for example, a specific heat capacity of a material. You could then reference a known specific heat capacity database and find out what the material was if you didn't know it before. That's a technique which is called calorimetry. It's used in chemistry. You'll see it in chemistry in your senior science chemistry, and it's used in physics also. But it can be used when you're given a sample problem. You might have to find a specific heat capacity or the mass or the change in temperature, but you would always just solve for the variable. Second type of question you would get would be one called the method of mixtures. So this is another experimental technique that's done by scientists, and we'll set up a scenario where we would dunk copper metal, which is warmer than a bucket of water, which is cold. So what happens if you put that warm metal into the cold water? Well, what would happen, of course, is that there would be an equalizing of temperature, if you like, and there would be a certain amount of energy lost from the copper and a certain amount of energy gained. Now, what you would notice is that, for example, if the copper started with a temperature of 100 degrees Celsius and the water was 10 degrees Celsius, for the first couple of minutes, you would see that there would be a temperature, if you had a way of measuring it, that the temperature value would actually be somewhere in between that. So it might be 40 or 50. Now, I should also say that we would really need this contraption or machine, or it's called a calorimeter in chemistry, a bomb calorimeter. We would need it to be insulated, heavily insulated, to make sure that there's no impact from the outside environment. So you would need a way of sealing that. Okay, so another way of looking at that, Q lost plus Q gained is equal to 0, is to say that the energy lost is equal to the energy gained. And one will have a positive, one will have a negative. So the energy lost, in this case, the energy lost from our copper is equal to the energy gained, the negative of the energy gained from the water. And so, of course, we can write it as MC delta T for those different materials. Okay, so we're going to look at the final thing we're going to do is just look at another sample problem. And that sample problem is thus. What mass of copper at 87 degrees Celsius when added to 300 grams of water at 17 degrees Celsius in a calorimeter? Remember, a calorimeter is just that sealed container that allows us to look at this as a closed system once those are added, would yield a final temperature of 26 degrees Celsius. So I'm going to ask you folks to make sure that you are aware that when we're mixing two different materials, we look at this equation. We no longer have the simple equation. The one to use is energy gained is equal to the negative of energy lost. You're going to set that up as an equation. You can use the specific heat capacity values of water and copper. And I would like you guys to actually practice subbing in those values to see whether we can arrive at a value to find out exactly what mass of copper, and do some investigative work and scroll backwards if you like and find out what mass of copper was added to the water. Okay, so I'm going to leave that ones with you. Hopefully we've seen that different materials react differently when thermal energy is added to them. We have an equation for that. We have a way of quantifying that. And that property is known as specific heat capacity.